Hello, it's me. I was wondering if after all these years you'd like to meet to go over everything. They say the time's supposed to heal ya, but I ain't done much healing. Hello, can you hear me? I'm in California dreaming about who we used to be when we were younger and free. I've forgotten how it felt before the world fell at our feet. There's such a difference between.
That was Adele, my co-teacher for the day. Hi, everybody. How are y'all? Again, um, lecture 3 of gas laws. And don't go in asking if there was any like weird gas law stuff or stuffed animal things. I want to get you really excited about more new and interesting stuff. So anyways, we're going to finish the unit today. Make sure that you have your kinetic molecular theory and real gas slides in front of you. No calculator, no periodic table today. Oh, not periodic table. No, I don't think you need a periodic table. And let's knock this out. Could theoretically be a quicker lecture. I guess we'll find out. So, all stupidity aside, let's do this. So KMT is not something new for you at all. We went over kinetic molecular theory in pre-AP. So this should be a revisit. Really, they're not going to ask you like, what is postulate 2 of the KMT? That's not going to be a question. They really come more in handy when, well, I would say multiple choice, but now there's not that this year, but we're going to keep using this video for future years. So on multiple choice, they might have you defend a statement using one of the different postulates in regards to if this is true about a gas, which part of the KMT supports that. But more commonly, it's going to be a part of the FRQ. Of course, your FRQ are multiple parts, A, B, C, D, and then usually one of them will say, all right, use the kinetic molecular theory to support this student's observation. And they want you to be able to pull in a couple of the postulates to describe a behavior. So we'll go through the postulates, remind you what they are, and then I'll give you a FRQ-ish question to ponder and see if your answer matches mine. So reading off of your slide, number 1, gases consist of tiny molecules which are in continuous random motion. All right, so we already know that all our phases of matter are in motion, solids being the slowest, and then gases having particles that are the fastest. So make sure you still do have that most basic foundation of that. Number 2, the distance between molecules is large compared with the size of the molecules themselves, which is basically saying that the gas particles, there's so much empty space in a gas sample that the particles themselves, the volume they're taking up, don't really matter. So that's an important part of the KMT, but it's going to be an even bigger part of the second thing that we'll talk about in this lecture. And then number 3, gas molecules have no attraction for one another. They have no repulsion either. But again, it turns out that while that's ideally true, the slower those particles are moving, the better chance they have for some kind of attraction to take place, because we've covered a bunch of attraction lately, right? When we went over in our last unit, intermolecular forces were a big deal. So you'll see that these two, number 2 and number 3 of the KMT, are the ones that are the fuzziest when we consider things that aren't ideal. Okay, you're begging for it. All right, bonus star. What's his name? Huh? What's his name? Put it in the comments. Go back to lecture 1. I told you his name in lecture 1. Ujo go cutie. Ujo go go scratch me. And then we've got the other three postulates of the kinetic molecular theory. Number 4, gas molecules move in straight lines in all directions, colliding with one another and the walls of their container. What postulate number 4 is doing is pretty much just defining pressure for you. All right, the definition of pressure is going to be force exerted on a surface. So it's just saying, letting you know that gases will be exerting pressure. Number 5, all the collisions are perfectly elastic. We don't cover that in AP. It's actually outside the scope of what they've said that they'll ask any questions on. The fact that they're elastic has to do with no loss of energy when they do hit one another, but there's no reason for me to waste too much of your time there because, again, we've been assured that postulate number 5 will not be covered. And then number 6, the average kinetic energy of molecules is the same for all gases at the same temperature, and its value is directly proportional to the temperature. That has to do with Ke. Now, an interesting thing about kinetic energy is that the equation for it, for calculating it, is on your AP sheet. That's a physics equation, really, but they've never, anywhere that I can find, ever asked you to use that equation. So it's always been asked for a conceptual standpoint. So speaking of the conceptual standpoint of postulate number 6, let's talk a tad more about it. Did you want to do it too? Come here. Come here. Up. That's a good girl. Oh, gosh. It's another animal video. Who do it? Who knew it? Oh, you know what's going to happen. You're a good girl. You're a good girl. You don't smell bad this time. All right, go see Mom. Oh, stop it. I'm being recorded over here, too. Anyway, okay, so postulate number 6, there's two things you need to keep separate from each other, and Schoology will actually give you quite a bit of practice in making sure you understand the difference between how kinetic energy is measured and how velocity is measured. So the only thing that's going to dictate a change in kinetic energy is going to be a change in temperature. That's what it's dependent on. So anytime we're looking at, okay, well, we have this gas and this gas both existing at this temperature, then they have the same kinetic energy. All right, there's the same total amount of energy available in that system. All right, what's different is the speed of the particles themselves, the velocity, and the speed of those particles is going to be directly connected to the mass of the particles. Now, this is called Graham's law, where smaller, or rather lighter, particles move faster. If you were in my pre-AP class last year, the example I used was if an elephant is racing a dog down the hallway, you expect the dog to be able to move faster. I might have used cheetah because then it's way more obvious, but a lot of times the smaller creatures have faster land speed, and that's kind of the idea of what you want to look at here. Now, Graham's law again states that lighter particles will have a higher velocity. There's an equation for Graham's law that has to do with using square roots, and it's really not a difficult equation to use. However, outside the scope of AP. So that equation is not on your AP sheet and won't be tested on. So I just want you to be able to connect the idea of Graham's law to the velocity of these gas particles. In the picture on the slide that I showed, it compares helium gas to ethylene oxide. And if you look back, I guess we can, all right, if you look back here, you can see that the particles of helium are effusing, all right, effusion being the passing of particles through a tiny opening. The particles of helium are effusing faster than the ethylene oxide. All right, well, why? Because Graham's law states that the helium particles, if you use the mass on the periodic table, are definitely lighter than the ethylene oxide. Therefore, they have the ability to effuse, pass through the tiny opening at a quicker rate. So those are the 6 postulates. What I want to do is give you an AP-ish, FRQ-ish question. However, I've altered the slides. So what you'll see is on this question that we're going to look at, I changed it to Lussig's law instead of Charles' law. Only reason I did that was because when I was writing this slide, I was looking at a recent AP exam, and I was like, oh, they did Charles Law, so Charles Law. Okay, well, since they did Charles Law, that's less likely they'll do Charles Law again, so I just picked a different one because now there's a greater chance that maybe they'll actually ask this one since it's been less recent. So what I want you to do is pause the video and see, first off, when I say Lussig's Law, you should immediately be able to think of the two components that are being compared, right? Because I told you, you need to know, you're expected to know, the scientists of the combined gas law connected to what their belief was. So hopefully it comes right to your mind, oh, Lussig is this goes up and this goes up too, or whatever it is. And then you need to be able to apply the postulates. So pause the video, see if you can write down the best possible explanation that you've got in you. And I'm going to find another song for my friends here to dance to. I'm just kidding. I'm done with them. But pause the video. I'm going to show you the answer right now, or what I wrote as an answer. There's my answer to that question. I wrote as temperature, man, this is backwards on my screen, so I want to actually be reading it to you. As temperature increases, the average kinetic energy of a gas increases. As kinetic energy increases, the particles collide more frequently with each other and with the sides of the container. Increased collisions is an increase in pressure. So you'll see what I've done is I've taken Lussig's association of temperature and pressure and used good words from the postulates of KMT to explain it in a way that makes the grader say, oh, the grader think this guy knows what he's talking about, or gal. Yeah. And that is half of the lecture. So for those of y'all that already wrote down your slides like you're supposed to before clicking on this video link, you know that the next slide says, boom, there's no such thing as an ideal gas. And it's true. The reason that we do ideal gases is because it's a great theoretical way to study the connection between pressure, volume, temperature, moles, and the way that they would ideally act if there wasn't other tiny variables that throw them off. But in real life, nothing is actually ideal. So we need to figure out why. Real gases, non-ideal gases, are going to be deviating from postulate number 2 and number 3. As I was introducing them a few minutes ago, I mentioned that those are the fuzzier ones because they're not true in the real world. For example, number 2, postulate 2 has to do with, well, the gas part, there's so much empty space that volume doesn't really matter. Okay, but the volume occupied by a gas is not negligible. Gases take up space. Gases are a part of matter. So by definition, they take up space and they have mass. Therefore, that should be a part of. It can't just be completely ignored if we're doing chemistry in the most honest way. Postulate number 3 stated that there is no attraction or repulsion between gas particles. And okay, but like I said when I was introducing that postulate, well, what about IMFs? I mean, because we know that we know that the potential for London dispersion and hydrogen bonding and dipole is there. And if that's there and there's any attraction whatsoever, then it breaks postulate number 3. So I was going to draw this on my whiteboards here, but y'all know how great of a drawer I am. I'm pulling up a chair, sorry. So what I tried to do is kind of summarize this whole idea of ideal versus real in my own way. Will you call this dog? Do you want her to bark? Get the kitty. It's Tom and Jerry at my house. Okay. Anyway, so pause the video, get it written down. I hope I can make this make sense the way that I want it to. But in comparing an ideal gas to a real gas, first off, I labeled the ideal as hypothetical, even though we've spent an entire lecture on it. And Pivnert, you're going to be asked to use it. But the real gases are the actual. So here's our main differences. In the ideal gases, we said that there's insignificant attraction. So if you see this dotted line, I've tried to split this terribly drawn balloon into two sections. But you can see that the particles are so far apart, all right? And the idea is that they're moving so quickly that that there wouldn't be a chance, an opportunity for them to have attraction, all right? So what would make them be far apart and be moving quick? Well, it's this down here that would allow that to happen, all right? So gases are most ideal when they're at a high temperature because the particles are moving faster, less chance of them having an attractiveness. And when they're at low pressure, all right, because if they're at low pressure, that means they would be at higher volume. And if there's more space, then they can be further apart and not attract one another. But in my real gases, IMFs, boom, boom, boom. All right, we know at the very least we'll have London dispersion. All right, and then depending on what other kind of what other atoms are making up the gas, you know that those stronger IMFs can exist also. Therefore, these particles, like these two guys right here, they can absolutely have even a brief London dispersion attraction for each other. And suddenly, we've broken the reel of ideal gas laws. All right, so again, for the ideal, it says the volume of gas particles is negligible compared to the volume of the entire gas because, there's so much empty space under our ideal rules. But again, particles do take up space. So if by definition they are taking up space, then just making this huge assumption that the volume doesn't matter is a falsehood of chemistry. So the real gases, or rather, I like to say that gases act the least ideal when you're dealing with a low temperature because the particles have slowed down. All right, the kinetic energy has dropped. And now, hey, if they're moving slower past each other, they have a greater chance for an IMF to come into play. And then at high pressure, because if that pressure is high, that means the volume would be low and there's less space. They're going to be closer together. So there's this thing that summarizes an equation that actually summarizes real gases in a way to autocorrect, to make them ideal when you're calculating. Because if we're dealing with a gas that is not an ideal gas, and I was like, all right, if the pressure is this and the volume is this, then find the temperature, and you try to use Pivnert, well, suddenly you're like, but wait a second, some of the assumptions that we make in Pivnert aren't true. It's not. We're looking at a real gas here. So there's an equation to fix it. The good news is you don't have to use the equation. All right. You do need to know what the van der Waals equation is just in regard to its existence, but you don't have to be able to write it, and it won't be on the sheet. So if you want to pause the video just so you can have it written, just since it is good to have in your notes, I should have just put it on the slide. But anyhow, there's the van der Waals equation. And what I want you to notice about it, though, all right, is that you can see Pivnert living in there, but the pressure and the volume are being altered. It's doing an autocorrection because what you want is you need to add to the pressure. If you look at the equation, you'll see that it's P plus. Well, why are we wanting to make the pressure go up? Well, because suddenly there's attractiveness in the real gas. The particles, instead of just bumping up against that the walls of the container, they're being attracted towards each other. All right, which is going to be lowering the pressure to a level that it's not supposed to be at. So we can add a specific factor in a mathematical way that you don't have to do in order to make up for the lost pressure of this attractiveness that the ideal gases don't have. You'll notice that the volume of the van der Waals equation is subtracted. All right, the idea is that it's subtracting to make the volume negligible again. Suddenly the volume, the V, has gone up. Now it matters, whereas it mattered far less in the ideal gases. So what do? Well, we say we take that down. So the point, understand, the point of that van der Waals equation is to make a gas that's being real act more ideal. Questions? So again, what I'd like to do is give you an FRQ-ish question. This one actually was an FRQ, and so I'm going to flash it up. Pause the video right away because then I'm just going to show you the answer. But again, see if you can connect what you know about the two types of molecules in this FRQ question, and what I just told you about real versus ideal, and see if you can come up with something that would be graded as correct, showing that you've got knowledge. I know it looks like I keep picking him up because I want to show him, but he is laying right next to the computer. He's hungry. Jarvis. Oh, sorry. Okay, so pause. Here's my answer. I put, in the van der Waals equation, we add a correction factor to make up for the lost pressure due to the attractive forces between molecules. All right, so that's just a statement showing the grader that I know what the van der Waals equation is without having to write it or use it. HCl has stronger IMFs than H2. We know that HCl is going to be showing dipole, will be going dipole-dipole. All right, it's not London dispersion because it is a polar molecule, and it's not hydrogen bonding because it's not NOF. Therefore, but compared to H2, to the hydrogen gas, which only has London dispersion, that's a weaker force. So the HCl is going to have a stronger attractiveness, making it less ideal. Then I put also in the equation, we subtract the correction factor to make up for the additional volume due to the larger sizes of real gases. All right, so now once something is taking up more space and making the volume count more, that's going to be taking away from its idealness. So I can just do another, it's going to be pointing to the same answer, but in this case, the HCl is larger than the H2. All right, just use your atomic radius trend. It's larger, therefore less ideal. So in a perfect world, this would be the last lecture I have to record at home because I think, oh no, they added weeks, maybe not. Oh wait, no, there's going to be more.